Welcome to the Explainer. So today, we're going to decode the secret language that powers just about everything, from your favorite video games to some of the most complex scientific research out there, linear algebra. Have you ever wondered how a computer can juggle millions of problems at the same time? Well, it turns out they use a special kind of math that organizes information into these neat, incredibly powerful blocks. So let's dive in and start learning the vocabulary of this language. All right, so here's what we're going to cover. We'll start by learning the alphabet of this language. Then we'll see how to form sentences to solve real-world problems. And finally, we'll uncover some of the deeper grammar that gives it all its power. At its heart, linear algebra is really the art of handling huge systems of information. It gives us this amazing framework to see patterns and solve problems on a massive, massive scale. Okay, so before we can start building anything, we've got to know our materials, right? And in linear algebra, it all boils down to two fundamental concepts. First up, we have the vector. Now this isn't just a number. It's a number with a purpose and, crucially, a direction. Imagine someone tells you to walk 10 feet. That's not enough information, is it? You need to know which way to walk. That's a vector. It has both the 10 feet and the which way. Think velocity or force. And that is the key difference between a vector and something called a scalar. A scalar just tells you how much, like your speed is 60 miles per hour. But a vector, well, that adds the crucial direction. Your velocity is 60 miles per hour north. One is just a number, the other tells a complete story. So, what happens when we group all these vectors and scalars together? You get a matrix. It's basically an organized box of data. If a vector is a single instruction, then a matrix is the entire instruction manual, all laid out in a perfect grid. Okay, so you might be thinking, what's the big deal about organizing numbers in a box? Well, it's a game changer because it allows us to take a really tangled mess of equations and solve it with an incredibly elegant and powerful method. The first thing we do is just strip away all the variables, the x, y, and z, and convert the entire system into what's called an augmented matrix. Look at that! All the essential information is right there in one clean, organized block. Now, the name of the game here is Gaussian elimination. Don't let the name scare you. Just think of it like a systematic puzzle where we use a few simple rules called row operations to eliminate variables step by step until the solution basically reveals itself. So our mission is to create this triangle of zeros in the bottom left corner. We're going to start right here, turning this 2 into a 0. To do that, we use a simple rule. We multiply the first row by 2 and then subtract it from the second row. And just like that, boom, a 0, we've officially eliminated one variable. Now we just rinse and repeat this simple process for the other numbers down in that corner, just chipping away at the puzzle. After a few more of those steps, we end up with this beautiful, clean, triangular shape. This is called row-echelon form. And the real magic? It's right there in that last row. If we put the variables back in for a second, it's telling us that 0x plus 0y plus 1z equals -1. We've just found our first variable. Z equals -1. And from here, it's like a domino effect. It's called back substitution. We take that value for z, we plug it into the row above to find y, and then we use both of them to find x. We've solved the entire system by turning a complex problem into a really elegant step-by-step puzzle. Okay, so now that we've seen how this stuff works in practice, let's dig a little deeper into the rules of this language. We're going to start with a very, very special kind of matrix.
Meet the identity matrix. Its job is super simple, but also incredibly profound. You know how multiplying any number by 1 doesn't change it? Well, the identity matrix does the exact same thing, but for matrices. It's the neutral element, kind of like the anchor point for matrix multiplication.
And this is what it looks like. See that clean diagonal of 1s? That's its signature look. It might seem simple, but it's the anchor for more advanced operations, like finding the inverse of a matrix. All right, let's start to tie this all together. It turns out we can actually analyze a matrix to understand its core properties. It's almost like learning to read its DNA. So, one of those key properties is called the determinant. It's basically a single number that summarizes the whole matrix's behavior. Why does that matter? Well, for one, it tells us if the matrix is invertible, which is crucial for things like undoing transformations in computer graphics. And if that determinant is 0, whoa, that's a huge red flag. It tells us our system of equations doesn't have a single unique solution.
That red flag is a condition called linear dependence. All it really means is that some of the information in the matrix is redundant, it's repetitive. One row is just a scaled-up version or maybe a sum of the others. The equations aren't truly distinct.
And that idea of redundancy leads us right into our next concept, rank. The rank is simply the count of the truly unique independent rows of information. It cuts through all the noise and tells you the real substance, the true dimension of the data hidden inside the matrix.
Take a look at this matrix, for example. Yeah, it has 2 rows, but look closer. The second row is just the first row multiplied by 2. So there's really only one line of unique information here. That means its rank is 1, not 2.
Now, all of these concepts, determinants, rank, they all build towards even more powerful ideas, like eigenvalues and eigenvectors. In a nutshell, these are like the hidden axes of a matrix, the core directions that don't change, even when the matrix is stretching and rotating everything else around them. These are absolutely essential for everything from facial recognition to physics.
You know, we've really just scratched the surface of a language that literally describes our digital world, from graphics and data science to quantum mechanics. Now that you know the basic grammar, the question is, what problems are you going to solve? What will you build with it?